Hello and welcome everybody. I'm Nate.Budryk, Content Manager at Super Radiator Coils. For today's video, we're going to be discussing ASME Section 8. We're going to touch on kind of what it means to us as engineers as well as a manufacturing company, and we'll also touch on the benefits to the end user, so in this case, our customer. So let's get into it. Okay, so joining me today are Brian Biskie, Adam Horntvedt, and Harrison Waneck. Brian comes to us from SRC Richmond. Adam works out of our Minnesota office near Minneapolis, and Harrison sits in our Phoenix operation. Guys, why don't you go ahead and say a little bit more about yourself and introduce yourself. Let's start with you, Brian.
Yeah, hey everybody. So, I'm a senior sales application engineer with Super Radiator Coils. I work out of the Richmond plant. I bring 14 years of experience. I've been with the company for about 10. And my specialties are power generation, process, pulp and paper, and as all of those things apply to ASME.
I'm Adam Horntvedt. I've spent the last couple of years here at Super Radiator, some previous experience at a boiler company, and then 5 years additional experience designing industrial furnaces. My focus is primarily on industrial heat exchangers.
Hi everyone, I'm Harrison Waneck. I'm the Senior Sales Application Engineer here in the Phoenix location. I started off my career designing subsea wellhead equipment, and then after a few years switched over to the heat exchanger business, where I worked for a company manufacturing air-cooled heat exchangers and then hairpin and shell and tube exchangers. And I've been now with Super Radiator Coils for about 6 months.
Right on. Well, welcome, guys, and thanks for doing this. Let's jump right in. We're going to talk about some ASME Section 8 background and some terms you may see along the way. So the American Society of Mechanical Engineers, ASME, obviously was founded in 1880, and it began to kind of issue preliminary standards for the construction of boilers. The Boiler and Pressure Vessel Code, of which Section 8 is a part, specifically can trace its roots back to 1907 after a series of deadly boiler explosions, most notably at the Grover Shoe Factory. Some of the incentive, devastating incentive as to why these kinds of standards came to be a necessity and why there's so much importance placed on them today. So the Boiler and Pressure Vessel Code today is comprised of exactly 12 sections, so one of which is Section 8, which we'll be talking about today. And it's kind of all interconnected. There's some pulling in from other sections that may affect Section 8, and we'll touch on that later on in the presentation. Like we just said, here are the 12 sections of the ASME Boiler and Pressure Vessel Code. Section 8 we have called out here, and you'll see that there are 3 divisions within it. And we'll also touch on that as well. So, okay, for this one, I'm going to turn it over to Adam for some more terminology and background. Why don't you go ahead there, Adam?
Right. So Nate mentioned that this pressure vessel code has been around for over 100 years now. So it's evolved, and can be considered a mature code at this point. However, they still release additions every 2 years. This allows for new technology and material science, new welding procedures to be incorporated, and also allows them to make any corrections or modifications to the analysis. For many parts of the code, much of it looks the same as it did back in the 70s and 80s as it does now, aside from minor formatting changes. So with Section 8, we have U and UM stamps. This is on the nameplate of the vessel. Other sections have other letter designations, such as a letter S for Section 1 steam boilers, letter N for Section 3 pressure vessels for the nuclear industry. Right now, our current edition is 2019. The new edition, 2021, is being released in July, which then comes into effect in 2022, January 1st. So for the sake of brevity for this discussion, we're focusing on ASME Section 8, specifically Division 1. Division 2 and Division 3, we're not going to go into too much detail. But section 1 is kind of a recipe-based equations for design. Section 2 gives design engineers more leeway to design around specific applications that don't fit the code as well. And then section 3 is for high pressure vessels over 10,000 PSI. So we may, for shorthand, be saying ASME, section 8, pressure vessel code. We're all referring back to section 8 and the incorporating supporting sections, section 2 for materials, section 5 for non-destructive examination, and section 9 for welding and brazing. I mentioned UM, and if we can go back, Nate, for a second. So section 8 has 2 stamps, U and UM. The UM stamp is for smaller, lower pressure vessels where the inspector witness of the hydro test can be waived by the manufacturer. And that's listed on the slide here for pressures under 600 PSI for varying volumes of vessels. So section 8 is considered the general pressure vessel section, although it's not inclusive. So right off the bat, it goes into details what section 8 does not cover. Listed here, obviously vessels covered by other sections, so boilers, vessels for the nuclear industry, some other things such with rotating equipment like pumps, turbines, and engines, piping components, pipe fittings that are covered by ANSI standards. And then if we can focus on the I exemption, vessels having an inside diameter, width, height, or cross section not exceeding 6 inches and no limitation on the length of vessel or pressure. So for us making heat exchangers, that covers the vast majority of our products are outside of the scope of this pressure vessel program. That being said, Section 8 does allow you to stamp a vessel that is not strictly within its scope so long as you meet all the requirements set forth in the standard.
Got it. Brian, you want to take this one?
Yeah, so strictly speaking, ASME is not a law, but it's common for ASME boiler and pressure vessel code to be a flow down requirement from building codes, insurance carriers, customer expectations, or industry standards. So typically vessels that you might see in heavy industrial applications like power generation, chemical process, and pulp and paper sometimes is where you'll see ASME required the most often. What we've seen is some military applications on a case-by-case will accept ASME in lieu of NAVC, TechPub, or mill standard vessels. But it doesn't cover all industries. So if you're working with HVAC or refrigerated display cases or other lighter duty commercial applications, you're going to see safety standards other than ASME, such as UL, ETL, or CSA. And, you know, if you're looking at other countries or if you're exporting to other countries outside of the US, it's common to see safety standards in addition to ASME, such as the Canadian CRN. European uses the PED CE mark. Russia has their own called GOST, and, you know, several others depending on what country you are exporting to. So we could use our experience to kind of help you navigate, or at least help you find where to look to see if ASME is a requirement. And we can also give you the information to make a decision if you'd like to include ASME for safety purposes, even if it's not a requirement.
Got it. Awesome. Okay. All right. So let's move into a little bit. We just kind of, we've started the discussion here, but let's talk about specifically what ASME Section 8 is. So Brian, why don't you keep going on this one there, sir?
ASME Section 8 is kind of like a cookbook of safe design practices. So ASME provides lists of materials that are allowed by code, and it provides the properties of those materials that you can then use as inputs to the equations for designing your vessel. So the materials are kind of like the ingredients, and the design equations are kind of like the recipe. And by doing that, ASME standardizes the factor of safety in these designs. I think it's approximately 3. I know it changed a few years ago. So we use these formulas to figure out what the thickness of the parts are, hole sizes, hole spacing, the joining processes, any forming of parts, and then also the types of documentation that we need to be able to demonstrate compliance with the program. Now, every once in a while, you'll run into a specific geometry that's not covered explicitly by the code. There might not be a formula for a refrigerant distributor on how to calculate the thicknesses, or there might not be an explicit formula for a special type of piping flange that's outside of the ANSI flange family. And in that cases, we can use finite element analysis and other means of calculation to demonstrate acceptability of our design to our authorized inspector.
Got it. Okay. So it sounds like there are a lot of exceptions, and you need, a partner is definitely advantageous when navigating kind of that water, because there are
certainly, yeah. I mean, there's a lot of things that are kind of cookie cutter that are covered explicitly by the code, where you can just find the formula and put in the inputs and get the answer. And then there's a lot of other things that the code is silent on and not explicitly addressed. And all of those refer back to basically a paragraph that says you discuss with your inspector, and with his concurrence, you can proceed.
Got it. Okay. All right. So moving on to kind of the material side of things, Harrison, you want to go ahead and tackle this one?
Yeah, that was good. So what else does ASME encompass? So any sort of pressure boundary or pressure containing component for a Section 8 vessel must be using material recognized by ASME Section 2. And a lot of times these material standards are based off of ASTM, an equivalent material, but it also should be recognized that just because it's an ASTM material spec does not mean it's governed under the Section 2 recognized material list. And what are you getting when you select a material under the Section 2? So a lot of times it'll govern things like chemical composition. So like if you're choosing like a 304L or a 316L material that's easily weldable based on material composition, you're getting things like geometrical tolerances, like thicknesses of plate, roundness of tubes. And all those things are really important when you're trying to design a high quality vessel. And you get things like heat treatment, like if you're getting like a normalized steel that's like Hick resistant or gives it properties that are, more resistant to cracking. You also get like testing qualifications, which, you're going to have like Sharpie impact or hardness testing on the material that you're going to make sure that it meets up to those standards specified in the Section 2. And as I said before, it should be noted that not all materials are recognized by ASME. And just because there's requirements based in Section 2, that doesn't mean that also based on the applications that I mentioned before, like a NACE application, there can't also be additional requirements added on to the material specifications. And Section 2 also will give you allowable stress values that you will use in your design to calculate your minimum material thicknesses.
Yeah, so I mean, this is a big deal, pretty clearly. I mean, these are important calculations and have huge impacts when it comes to the unit, and then largely the system and the safety related to it.
Yeah, I mean, a lot of times material selection is kind of your stepping block for start one, right? I mean, it's once you select your correct material in your application, then you can kind of work through your design and start from there.
For sure. Okay. Harrison, I believe this is in your ballpark as well.
Yeah, so ASME is a quality standard. It doesn't only encompass how to calculate the stress, where to get the stress values from, like the material selection, but it also encompasses all the processes, including like welding. So anytime there's a worker that's like doing any braze work or any weld work or any other processes on an ASME vessel, they have to be tested and qualified per ASME guidelines. So they'll weld up like a test coupon, and there's numerous different qualifications they'll go through and inspect the weld to make sure that the welder meets up to qualities and lack of defects within the weld. ASME also establishes rules for post-weld heat treatment for certain types of welds and certain types of materials. And again, that's just to ensure quality of the product and make sure that there aren't any residual buildup stresses in those weld joints. And also, depending on the weld joint, ASME may require some sort of non-destructive testing, whether that be ultrasonic, X-ray. Shown in the pictures to the right, you can see an X-ray machine taking an X-ray of a butt weld on a pipe there. Or liquid penetrant or mag particle, and it really just depends on the configuration of the weld. And also, an important thing to note too in your design is what's your accessibility to the weld. So if you can't X-ray it, can you UT it? So there's a lot of plug and play there with the configuration of the weld. There's a lot of consideration that goes into the design of that when you're selecting your welds and how you're going to inspect them to ensure quality.
Got it. Awesome stuff. Okay, and so kind of all that to say, kind of basically what we've covered up to this point is this is basically the benefit to in our case SRC customers. So Adam, do you want to kind of take this one? I know it's not so easy to reduce 1,600 pages to 2 bullets, but this is our best shot.
Well, exactly. So Brian discussed how ASME regulates the design, the engineer's design of the pressure vessel. Harrison discussed how the material, the supply materials, and then the joining practices, the manufacturing, and this inspection is all carried out. To what end? Well, essentially to reduce the risk that there's a failure of a pressure vessel, which can cause harm to equipment or personnel. So that's primary function. It's why ASME was created, to reduce the risk of a failure. Now, also an advantage of that is it increases reliability. So if an owner-operator has a critical piece of component that, if it fails, it shuts down the whole production line, well, that's a consideration that some people will put into play to require ASME stamping of a pressure vessel, where it otherwise may not be required by code.
Got it. Okay, nice. So we've outlined what it is, and then kind of all of the pieces that go into it. But there's also an equally important discussion to have as to what ASME does not cover and what it doesn't pertain to. And so for that, we're gonna, I think, Brian, this one will go to you. Just kind of some the fact that it's a non-industry specific standard and what maybe some examples.
Yeah. So we touched on a little bit of this. So ASME is not specific to any one industry. It's an independent body that provides safe design rules for pressure vessels. So for specific applications or some other customers, we might see standards that are applied either in addition to ASME or instead of ASME. For example, a couple that we have up here, TEMA, mostly addresses or entirely addresses shell and tube heat exchangers. We see it applied somewhat to our air coolers, and anytime that we have tubes coming through a tube sheet, that style of manifold will often reference TEMA as a technical standard. API, same kind of deal, specific to oil and gas. It gives guidance also on welding and material selection and safety. If you get into some military applications, you'll see NAVC, MIL standards, tech pubs, etc. And one of the really useful things here is that even if ASME or one of these standards is not explicitly required for your project, they are available as a technical reference, and we use them often. I remember I was working on a pretty high spec project for a chemical process, and it was very critical that all of the tubing bends meet a very high quality standard. So we were able to go to ASME, and we were also able to go to TEMA. Both of those codes give some guidelines for ovality of tube bends, the thinness or the thinned part of the dose, or any wrinkles on the intradose, and they give acceptance criteria for that. So In that instance, neither TEMA or ASME was explicitly required, but we were able to reference those as a technical standard to get the quality that the end use required. So there's a lot of flexibility, and it's not specific to any one industry.
For sure. That kind of speaks to it being a living, kind of breathing entity. It changes frequently. It often pulls in from all these other places that we've covered. There's a lot going on. It suffices to say. And then on kind of the legal side of things, Brian, if you want to stay on this one.
Absolutely. Yeah, so, in the U.S., and I think abroad also, ASME is not a legal requirement. It's found as a flow-down requirement from building codes or fire protection codes, insurance carriers. It's different, actually, in Europe. Europe uses the CE mark and the Pressure Equipment Directive, and that is required by law. So that's a national standard for them. For us, it's required a lot of the times on these big industrial applications through these sub-tier flow-down requirements. So kind of an important distinction to make here. We've got two bodies, right? We've got ASME. ASME provides the rules for constructing a safe heat exchanger. And then we have the National Board. These two bodies are by and large independent. The National Board is the enforcement. So the National Board is who Super Radiator as a company, we went to the National Board with our quality system, and the National Board reviewed our quality system, and we were able to apply to get these authorizations to mark. We call that our UM stamp, our U stamp, N stamp, S stamp, etc. So that's provided by the National Board. When we get into making the actual heat exchanger for your application, then we demonstrate that our design meets ASME, and that design is then reviewed by either our authorized inspector or a certified individual for compliance with ASME. And our authorized inspector, they work for our insurance carrier, and they are licensed by the National Board to inspect vessels on their behalf. So the process, kind of how this all fits together, it has global adoption. There are a lot of countries that even if they don't specifically use ASME, their pressure vessel standards reference ASME or are built on a similar format to make their individual standards. So there's a lot of quality oversight and multiple bodies, and that's what keeps us safe.
Yeah, by design, right? You have layers of oversight and upon layers of oversight, for example. Yeah. You described, so for sure. All right, well, thank you, Brian.
Yep, and ultimately, even with that oversight, ultimately the responsibility is on the manufacturer, and we take that very seriously. That despite these checks and these verifications, which are great, at the end, it's on us. So, and that's a responsibility we take seriously.
Absolutely, no doubt. Okay, and then so for the next section, it is not a performance standard. So Harrison, do you want to touch on how this ASME it does not pertain in any way to heat transfer performance?
Yeah, thanks, Nate. I think this is like one of the most important points, when we talk about what ASME is and isn't. ASME is a quality standard, which we've been outlining before, and it basically dictates quality for your pressure vessels and your boilers, right, with how they're constructed. But it doesn't pertain to any sort of thermal performance as it pertains to like a component or on a system level. There's different organizations that govern standards like that, like AHRI and ASHRAE. So AHRI is the Air Conditioning, Heating, and Refrigeration Institute, and ASHRAE is the American Society of Heating and Refrigeration of Air Conditioning Engineering. And for those, really, this boils down to, a company can make an ASME vessel, but when you're having someone look at your process or your thermal design, it really stresses the point to come to somebody who is going to be able to help you and look at your process and give you a solution that works, not only on your construction side, but what's going to thermally work for you and your system. And I would recommend myself and any of my other colleagues at SRC are more than capable to provide you the design that works for your system thermally. So I think that's also an important thing to note too, is that just because your vessel has an ASME stamp, that doesn't mean that it's gonna work right for your process. It just means that it's been constructed to those standards. So I think it's a really important note to have.
Yeah, absolutely. Totally agree. Okay, so moving on, we're going to just give a little bit of background about SRC and some of the work we do. We're a custom coil manufacturer. We make coils for a range of industries like the ones listed below. We have plants in Richmond, Virginia, where I'm at, Minnesota, where Adam is, and Arizona, where Harrison is, in Phoenix. Brian is in Richmond with me as well. You can see some of the brands that we serve there. But so these are the kind of heat exchangers that would be probably likely candidates for ASME, depending on the application. These are your bulkier, process-oriented chemical plant type applications, and we specialize in those. And the three folks that are on this call here are experts in their construction and their relevance to the codes that we just covered. We also do light commercial HVAC. We do all sorts of air handlers. These coils will be used in air handlers, rooftop units, all across, hospitals, schools, commercial buildings, things like that. And then on the kind of more specified niche stuff that we do is nuclear products. And there is an ASME code section that pertains to this as well. We probably touched on it, section 3, I believe, if I'm not mistaken. And these are all safety and non-safety related heating and cooling applications for nuclear power plants. Some pretty cool stuff that they do up in Adam's location. And so, if you have any questions based on what you heard today, or would just like to know some more, or you find yourself kind of considering whether or not to start out on that ASME journey for your equipment, give us a call at one of our 3 branches. We can, together, our engineers have a ton of experience, and I highly doubt there's somebody between us that can't answer your questions. So with that, I'd like to say thank you to you for watching, and thank you to our presenters, Adam, Brian, and Harrison. Appreciate you guys doing this, and let's do it again sometime. So thanks everybody for coming.
Thanks, Nate.
Great.